a natural gas pipeline DN 400 with 10 mm wall thickness transports 3.2 metric 3.2 million meters cube per day. The specific gravity of the gas is 0.6 and the viscosity is 0.0012 pounds. Calculate the value of the Reynolds number, assuming the base temperature and base pressure are 15 degrees C and 101 kilopascal respectively. Now, let's begin. The Reynolds number is equal to the density of the gas at that condition times the velocity times the internal diameter of the pipe divided by the viscosity of the pipe. Now, but we are given the flow rate. We are not given velocity. Now we also note that the flow rate is equal to velocity of the gas at velocity of the gas times the cross-sectional area. So that means the velocity is equal to the flow rate divided by the cross-sectional area. And the formula for cross-sectional area is equal to pi d square all over 4. Now substituting this pi d square all over 4 into this equation, you now have u to be equal to 4 times the flow rate divided by pi d square. So having gotten this, now we also know that in field flow rate is always being recorded, being measured in standard meter cube per day. So this expression, the Q, is a flow rate at that condition, at the condition of the gas. Now for the condition of the standard condition, the flow rate as standard condition, for us to also relate it with the flow rate of the gas at any condition, we now have to apply the law of conservation of mass. Now, if you have flow, gas is flowing into this point and is going out. So the mass of gas coming in from here is equal to the mass of gas here. Invariably also, if you have a particular gas inside this container that is concise, so now at various conditions, the mass of gas here remains the same, provided there is no gas in or gas out. So provided there's no matter that comes in or matter that goes out. So provided it remains like this, it is constant. Now also in this case again, if gas is coming into this place in this form and also leaving, now the amount of gas that flows into here is the same amount of gas that flows out. So that means the law of conservative. Now if let's say here is the standard condition and here is any condition, now the amount of gas at this condition is the same. The mass of gas at this condition is the same mass of gas at this condition. So in that case, and mass of gas is equal to the flow rate in volume, in volume, you can say in volume, this is in volume per day times, so the flow times the density of the gas. So that means mass is the same thing as density times the flow rate in volume. Now, having expressed this, we can now see empirically from the conservation of mass that the product of the density of the gas and the flow rate at any condition is equal to the product of the density of the gas at the standard condition and the flow rate and the standard condition. So this expression is now established. Now we're going to make use of this. We're going to make use of it. So now let me now substitute this equation. Okay, let me call this equation 1, this equation 2, this 3. Now I will substitute equation 2 into equation 1. So we've gotten velocity in terms of flow rate. So now we now have to introduce this into equation 1. So we're going to have density times 4q all over pi d square all times d divided by mu. So now we now have, in all we have 4 density times q d divided by pi mu d square. So this d will cancel out this. We're now left with 4 density times flow rate divided by pi mu d. So the whole equation now falls back to this expression. Now we also, from equation 3, we know that the product of the density and flow rate at any condition is equal to the product of density and flow rate at the standard condition. So we're going to replace this with 4 this density at the standard condition times the flow rate at the standard condition divided by pi mu d. So we have gotten this whole thing in this form. Now when you check the value given, density was not given. Now we need to now change this density in the form of, so now let me just write that we have gotten the fourth equation. So this is the fourth equation. Now on the information given, density is not given. So now we are going to use real gas equation here. So real gas equation, pressure, the product of pressure and volume. Now in this case, this one is at the standard condition. is equal to Z, there is a compressibility factor at the standard condition, times N, that is the mole, times R, which is the gas constant, times T at the standard condition. These are all our standard conditions. So we now have pressure times volume times ZP times, now the number of mole is the same thing as the mass of the gas at the standard condition divided by the molecular weight of the gas times R times TB. So we also note that density is equal to mass divided by volume. So invariably, now what we're going to do, let's call this equation 5. Now for this equation 5, divide both sides by volume. So we are going to divide both sides by this volume of the gas. So we have pressure times P divided by VB, ZB M divided by VB times RTB divided by molecular weight of the gas. Now, also note that ZB is equal to 1 at the standard condition. So we're going to replace this with 1. So, and we're going to replace this with density. So this with density. So here we'll cancel out this. You have pressure equal to now density times RTB divided by the molecular weight of the gas. Now we also note that gas gravity, which is given, is the same thing as the molecular weight of the gas divided by the molecular weight of air. And the molecular weight of air is equal to 29 grams per mole. Now, substituting that here, we have, now rearranging this equation, you have the molecular weight of gas equal to 29 grams per what? Mole. So that is this information. We can substitute this expression into this equation now, but before we do, let's now make density here this the subject of formula. So now we now have density equal to pressure times the molecular weight of gas divided by RTB. Now substituting the molecular weight of gas with this expression here, we now have density equal to 29 ppg. So this is in grams per mole. So now divide by RTB. So we've gotten this. So now we can now substitute this equation. Can I call this equation? This is 5, 6. Now we can substitute the, the expression for density into equation 5, which is no, not equation 5, into equation 4, which is this. That means Reynolds number is equal to this is 4 density times flow rate divided by pi d mu. So now we're going to replace this density with this. So we have 4 into 29 ppg divided by r tv times qb all divided by 5 d mu. So we have this. So we have this. So now we can now rearrange this to be let me just do it the next. So we can now rearrange this to be 4 times 29. Okay, let me just bring it here back again. Let me just say ppg divided by rtp qb divided by pi d mu. This is the same as 4 times 29 times ppg times qb divided by r pi d mu tb. So we have gotten this now. Now, for us to calculate the Reynolds number, let's now write down the given information. So the given data is now they gave us outer diameter, which is 400 millimeter, and they gave us wall thickness to be 10 millimeter. Now from here we can now calculate the internal diameter. So internal diameter is equal to outer diameter minus 2 times t. So and 2 times t will give us what? This is 400 minus 2 times 10, which is 400 minus 20. This will give us 380 millimeter. So the internal diameter is 280 millimeter. Now we are also being given we're given the flow rates, although the flow rate always is given in standard condition, which is 3.2 million meter cube per day, and the gas gravity is 0.6. Now you have 0.6. Then we are given the viscosity to be 0.00012. poise. We are also given the temperature to be 15 degrees C, which is 15 plus 273. This will give us 288 degree Kelvin. So we need to convert it to absolute. Absolute temperature is what we're going to use in the formula. We have a pressure which is 101 kilopascal. We also have our gas constant to be 8314 grams times meter square per second square times Kelvin times mole. Now we also have, so these are the given informations. Now let's now calculate our Reynolds number. Now Reynolds number will now be equal to 4 times 29 times, let me just write down this. You have pressure, that is the base pressure times G times Q, is the flow rate divided by R times R divided by pi divided by internal diameter divided by gas viscosity divided by temperature, that is base temperature. So we have 4 times 29 times the pressure is 101 kilopascal. Now, 1000 Newton meter square is equal to 1 kilopascal. Now, times, so 29 times G, so this 29G is grams per mole. Grams per mole times, okay, G is 29G and G is 0. Sorry, G is 0.6. Now we have our Q. We have our Q to be 3.6 times 10 raised to the power 6. This is meter cube per day. Now we need to change this day to seconds. So now you have 1 day is equal to 24 hours. Now changing the hour to minutes, you say 60 minutes is 1 hour. Then changing the minutes to seconds, you have 60 seconds equal to 1 minute. So this minute will cancel out, this hour will cancel out, you have seconds left there. This gas constant is 8314 grams times meter square divided by second square divided by Kelvin divided by mole. Now times what? Pi times D, which is what? Sorry, well, let me write the value here. D, which is 380 millimeter. Now to change this millimeter to meter, you have 1 meter is equivalent to 1000 millimeter. Now we have the viscosity of the gas, which is 0.00012 poise, and 0.1 Newton seconds divided by meter square is equal to 1 poise. Then the next is times 288 Kelvin. 288 Kelvin. So this Kelvin will cancel out this Kelvin here. And this grams per mole will cancel this gram per mole here. We have millimeter will cancel out millimeter, poise will cancel out this poise here. Now we are left with, this is meter square times meter, as meter cube. So this meter square we cancel out this meter square here. We are left with meter. Now you have seconds square will cancel out 1 second square here. Now let's go up and see Pascal will cancel out this Pascal here. Day will cancel out this day here. We have seconds left here. We have now meter square will cancel out 2 meter square here, have 1 meter square here now. Now for up we are left with Newton meter per second. Then we are left with Newton meter per second. So now that means the Reynolds number will now be up here. You have 4 times 29 times 101 times 1000 times 0.6 times 3.6 times 10 raised to plus 6 and divide by this other one. This you have 224 times 3600 times this is 8314. This is times pi times 380, this value here, divide by 1000. So meter divided by 1000. Sorry, let me remove this meter here. Divide by 1000 here times this is 0.00012 times 288. Now here we are left with Newton meter per second. Here we are also left with Newton meter per second. So this will cancel out. So see, this is dimensionless. So now we have Reynolds number equal to 4 times 29 times 101 times 1000. Now there is one, this is divided by 1000. So this 1000 up here will now be 1000 square times 0.6 times 3.2 times 10 raised to plus 6. This is not 3.6, it's 3.2. Let me see the Q, 3.2. This is 3.2. Now 3.2, so divide by 24 times 3600 times 8314 times pi times 380 times 0.00012 times 288. So now let's calculate the Reynolds number. Let's now use our calculator. Applying our calculator here, we now have to calculate now. So we have 4 times 29 times 101 times 1000 square, then times 0.6 times 3.2 exponential 6 divided by 24 divided by 600 divided by 8314 divided by pi divided by 380 divided by 0.00012 divided by 288. So we have 7.59. Okay. There is an omission here. Let's see. There's an omission. There is an omission. I omitted 0.1. This 0.1. Let's times 0.1. So I omitted it. So see, it was 0.1. So that means the calculator, this value we minus, so we got here, I need to now divide it by 0.1. So we have 7.59. So we have 7.59 times 10 raised to power 6. So this is our final answer. Thank you for watching to the end. Have a nice day.